Hello. I'm Markus, and I will be talking to you today about machine learning projects and mainly about data. And a short intro about myself, who I am, and why I'm talking about this. I have a background in bioinformatics and predictive analytics in healthcare, after which I co-founded a machine learning agency called MindTitan, in which I worked as a data science lead in various industries and in various areas of machine learning. And we've also done consulting in public and private sector. Mainly what we do is we solve machine learning problems for other people. And in this work, I've encountered a lot of different issues that different organizations and people are having when they are thinking about machine learning problems. So today, I will talk to you a bit about the process in general, but we'll be focusing mostly on data and what you can do to improve the success rate or just improve the flow of the project in general. And most of the confusion that comes for people with machine learning projects is that they are inherently different from most other types of projects that people have to deal with, especially because data science is often relegated to IT departments, and because in IT projects are quite definitive, so that you know what you're going to get, you can make estimates, it's all right. But with machine learning, the main problem is that data science is very vague. And what I mean here is that you can't really predict that you're going to get results for sure. If someone tells you otherwise, they're probably either inexperienced or they're lying. And this makes things like really complicated for people who aren't used to these kinds of projects. Because so when you're starting out with a machine learning project, there are a few things that you can go through before you even decide that you're going to go forward with this project. It's first, of course, is that have you tried everything else? Meaning that in a lot of cases, people think that they need to use machine learning, while at the same time, it might be maybe more cost effective to have a person do this small task. Maybe it's checking some documents. A machine could do it. You could build a machine that can check those documents, validate them. But at the same time, you have to do it like twice a year, and it takes a person 2 hours. So it's probably a lot easier to just have the person do it. And then there are the two rule of thumb questions that you can ask about your project. First is it a limited scope issue? This means that, like, if you think about the problem, do you think that if you were given unlimited amount of time and unlimited capacity, like brain power, then could you solve this problem? Like, could you think of a solution given the data that you have? Because machines are faster than we are in numeric calculations, and they also have a larger capacity for like tabular data or images or whatever. So if the problem fits the criteria, then it's likely that machine learning can help you. The other is that it's a scalability issue, meaning that it's a problem really simple, but you just don't have the scale, like you don't have the people to do it enough. So for example, like the classic example of image recognition, like recognizing cats or dogs or tables and chairs. For a person, this takes milliseconds to understand which it is. But annotating thousands of hours of video with these kinds of tags is infeasible to have people do it. So in that case, as the problem is simple enough, you can probably have a machine do it, and it's easily scalable. And the fourth one, which I wouldn't really recommend, but because you can't trust people and what they say, but it's something to think about, is that have other people done it successfully? If it's, for example, recommendation engines, you see them everywhere. So probably recommendation engines is something you can do. But like if you think about some more complex problems, specifically domain-specific image recognition tasks, then if you can't find an example where people have done it, it doesn't mean that it's not doable. And if you find people who say they have done it, it doesn't mean that it's doable. But if it's common enough in the industry, then probably it can be done. But what's going back to the differences, like or the peculiarities of a machine learning project or a data science project. Although it's not exactly science, it is good to apply the scientific method here. And scientific method is agile by necessity. There's the formulation of the question and forming the hypotheses, and then basically you're training models, making predictions, testing the predictions, and using this, whatever you learned, as feedback to build a new type model. So, and you'll probably be going through this cycle many, many times, and the better you're prepared before you start this cycle, then the fewer of those you have to make. If we're talking about this in a more business process terms, then it's more like project inception, task specification, you develop a proof of concept, you test it, and then in this development maintenance part, this is where you actually go to the iterative cycles of improving the system by analyzing the results, giving feedback to the model prediction, model development, and going over and over like this. But as you see, that all of it kind of starts with project inception and task specification. And for that, the most important part here is asking the right question. Why I'm really focusing on this as well, because before going to data, is that this is probably the most important part of what you can do to help your machine learning projects, and also. This is like these two steps, like the question and the data, are the most in your control before you actually start doing any machine learning. So the important part is that you have to ask the right question. The question has to give value to the business. You have to understand whether it's how difficult it is from the machine learning or technical perspective. Maybe deployment might be an issue, and also the urgency of solving the problem. How critical it is to your business. And you'll basically be weighing the potential value and the urgency against the difficulty to understand if you really should do this project, or like how important it is to get it done. It might also turn out, if you analyze the difficulty, that it's simply like almost infeasible, or the accuracy you need is infeasible, and then you might decide that you don't need to do it at all, which is a very valuable thing to understand before you embark on the process. And also, like if you haven't covered the question that you should be asking, then this question should be in front of everyone's mind during the whole project. Because what can happen sometimes is that people start solving problems that are not exactly the question you're trying to ask, but they are kind of easier to answer with the data you have at hand. So this should be front and center on everyone's mind, and often repeated and reminded to people. But when we go to the data, like things you can do to check if the data that you have is actually useful for what you want to do. So most important part is, like, do you yourself think that you have what you need? Meaning that does the data you have enable you to, do you think that it enables you to answer the question you're trying to answer? I'm going to bring a few examples here. One of the first example would be like predicting demand for a product. We had a project now a few years ago where we were trying to predict demand, like the volume that is going to be sold in the market for a specific kind of product. On the graph, you see 6 years history of the sales of these products. So you can see from the data that it's very cyclical. It's a yearly cycle, and probably it's like relatively easy to predict it even from the sales data itself. But something goes a bit wrong in the last year. So this kind of breaks the cycle, and we would like to know why. In this case, we had good reason to believe that weather is involved in this process. So we also looked at weather data to see if there's any signal there. And on the graph now, you can see rainfall over the same time period. So yeah, we see that there is an anomaly in the sales data. We see that there is an anomaly in the same time in the rainfall data. So we have correlation. But what can we say about, like, do we know that there's a signal there? I would say that it's shaky, but if it's not too resource intensive to do this project, yes, I will give it a try, because like this fluke can actually be a fluke. If it's not like a new trend, then it probably won't be an issue. But what might be an issue here is that if you find a correlation, but it's actually not a cause, then the machine will definitely learn that there is a strong tie between rainfall and the sales of your product. So if like next year there's still a lot of rainfall, but the sales of the products like bounce back, then the machine will give you really, really bad predictions, because it's expecting the rainfall to coincide with the sales. But not all projects are time series projects. Like oftentimes, like most of what people do is in machine learning is most of the tasks are actually classification tasks. On this graph here, we're basically grouping, like what we needed to do is we needed to analyze each sentence a person says in a phone call and analyze what they're talking about. So to understand if this project is even doable at all, because like human language is really vague. How people talk, very vague. So we want to see if there are even like clear groups of different topics in like ways people speak in the data. So we try to see if there's any separation at all. So we can see that there's some separation, definitely. There are a bunch of different clusters, but we don't know if it's it's promising, but it's nothing really concrete yet. So we want to see if these clusters are actually on the same topic, or they are just maybe they're clustered by the way people speak or the words that they use, and not related to the topics themselves. So we labeled a bunch of them, and we saw that there are although there's quite a bit of confusion in the middle, there are still clusters that seem to be clearly of one single topic, different topics of the orange, the greens, and the blues. So from this, if you do a sanity check like this, you can say from this that probably the problem is solvable using machine learning. How do I how should I treat the confusion in the middle? Well, it's probably going to mean that it's not going to be 100% accurate. The problem isn't super simple, but classifying human language never is. So what I would take away from here is that yes, the problem is solvable, but it's not going to be a very short one. And the second most important thing, which even experienced people often don't get right or make mistakes with, is that is the data actually similar to the actual use case that you're going to use the algorithm in? So what we mean here is that do you actually have the training data, or that is from the same situation that you're going to use it in? If we're talking about recommendation engines, then when you have an e-shop, you have a lot of purchase history about the products and people, and you're going to use it in an e-shop in a similar environment, then yeah, you're good. This is going to be fine. With the previous example about calls, we are learning from calls to classify calls. Again, this is fine. But recently, what I had to do is I had to build a language classifier that works with audio and classifies Estonian and Russian into different classes. We started with two languages. Should be fairly simple to differentiate. They sound quite different. So I had a lot of data for Estonian phone calls, but I didn't have a lot of data about Russian phone calls. So what I did was I went online and got a few corpora in different languages. I had Russian, English, Spanish, German, just so the model would not just learn to differentiate between Russian and Estonian, but also learn what language is and what makes one language different from another. But in the end, what I wanted to do is classify Estonian and Russian. There's supposed to be a few audio clips here, but we replaced them with text for technical difficulties. So when I started to use it, the Estonian case, we see that it's quite clearly Estonian. The person wants to increase the data cap in their plan. In Russian, the sentence is topic is completely different, but But yeah, some of those came out right. And then in the Russian class, I also had like completely weird languages. I had basically everything there. And as you can also see, the topics of the other language texts are quite different because the source is completely different. And what it turned out is that what the machine learned is not to differentiate between Estonian and other languages, but it learned to differentiate between phone call and all other sources of data. So all other classes were like Estonian, detecting Estonian, super good, but then there was like everything else, which is clearly the case that I didn't use the data that I wanted to use the machine in. I needed to use it on phone calls. So if either of those previous ones were wrong, or even if they're like you answered no to previous two, you don't have signal in the data, or it's not really you don't have the right data for your use case, then, or even if you answered yes to both, then at some point you're probably going to need more of it. So the thing is that like how can you get more data, or the exact data that you need, and can you merge the process into what you're doing right now? Like, can you label data inside the business processes that are running already right now? This is the ideal case. So, how machine learning models commonly are trained is like for example in those again calls or chatbot cases, you have a customer asking a question. The person who talks with the customer or assists the customer labels it as, for example, like last invoice amount, and then these labels are fed to the classifier, which is then trained and then can at one point start answering those themselves or classifying those questions themselves. So ideally, what the process will look like is that it's a cycle where a customer support person talks with assists someone, labels it. Then there's like a second and third labeler who makes sure that the labels are uniform and similar, and because they have to be as accurate as possible. Like bad labels can ruin a model. These are stored in a database, and then every once in a while, a data scientist comes and checks them, not in the domain-specific issues like is it classified correctly or not, because they don't know anything about that. They're more likely looking at like what is a complex case, where do we need more labels because the machine is making mistakes, more stuff like that. So ideally you would have a process like that where the common process of like a customer support person is still helping the customer, but now they also are an AI trainer in the sense that they label data for the machine. This is the ideal case that you want to get, that you can label the data in the business process. As you get more of this data, you can, like, the classifier will be able to, listen to a call, classify people into a number of classes, and as you collect more data, it can help people better, like more accurately, and answer more detailed queries. And this is probably the question that I get asked the most. This is one of those things that comes up already in the first meetings that we have with the client. And the question is like, do I have enough data? And it's also like a super complicated thing to ask, or super complicated thing to answer, because or like I have a very unsatisfying answer to it. And the answer is that it depends, because it doesn't depend only on what kind of problem we're trying to solve. Are we trying to build a recommendation engine? Are we trying to build a speech recognition system? Or are we trying to recognize images? It also heavily depends on the problem itself. So what I mean here is that, like, if you have a more complicated or more detailed problem, it's going to need more data. But even then, like, all I can tell you is that this is way too little, or this should be fine, but nobody really knows. Like, for example, I mentioned speech recognition systems. Like, when we're talking about speech recognition, then state-of-the-art models are trained on 10,000 hours, like tens of thousands of hours of data. Like, we're talking about and Google and Baidu, Microsoft, like they have immense corpora of transcribed speech. So what they are doing, training very large models on huge amounts of data. What we have found that works reasonably well, like is for our cases, is a base model that is trained on 300 hours of data, and that can be tuned with 20 hours of data. When I say tuned, then I mean that it is adapted to either a specific set of topics, like for example, you use this model in court or in a hospital, then the vocabulary is going to be completely different. So you want to adapt it to the vocabulary. And the other thing you want to tune it for is the specific situation. For example, if you're transcribing someone reading a book in a really quiet room, then it's a completely different task from transcribing someone talking over a phone or giving an interview in a cafe. To machines, these scenario differences make a large difference. They aren't as well at generalizing or adapting as people are. And like, how large a difference does it really make? Well, here we're showing what I'm showing on the graph is word error rate, which basically means the percentage of words that are understood wrong by the machine. And these stats are about Estonian. So when you take the ideal condition model, like the ideal conditions being that, for example, I'm here in a quiet room talking to a microphone, then it makes about 17% of errors. Now you take the same kind of model and put it in a tricky condition, the tricky condition here being talking over the phone, then it's going to make an average of 45% of mistakes. That's basically every second word is wrong. Now you take you take some extra data and you tune it to the specific case, like both vocabulary and also for the scenario of talking over the phone with all its like noise, low audio quality, and you can get it back down to about 20%. So so there are like a lot of different numbers here when people ask me like how much data do I need? Should I say like tens of thousands of hours, or is it like 300 because they need a base model, they need a new language, or they need to tune the model? And also the 20 hours is not always sure. It depends on, again, on the language, it depends on topic. A lot of things are influencing here. All we can say is a ballpark, but again, when you look at those numbers, then these are orders of magnitude differences. So these kinds of ballparks we can give. And when you go to for example, you have this speech recognition model. Now you would like to route people, or like you want the machine to be able to actually help the customers, for example. Then how much data do I need then? Well, the first thing, like you can start small, meaning that you're automating an IVR system that just directs people to the correct customer support person. You have about, 10 classes. Then assuming that those classes are easily separatable, then you're probably gonna need data in the amount of like hundreds of labels. When I say easily separatable, then I mean that the way people speak about them is quite different. Like if you look at the list of classes that are on the slide right now, then there's like billing and debt credit, which can get confusing because like probably people are going to use similar words when they talk about both of those topics. But other of them, like getting a different, like for example, tech support and billing are probably going to be quite easily separable. What that would mean, if they aren't easily separable, is that you will need more labels in the billing and debt credit for the machine to understand, like what is the thing that actually makes those things different. Like if you collect more data, then maybe you can already direct people to, like you can have a chatbot answer them. Why it requires more labels is that you need to be more certain, and you also probably, if you want to actually help people, then you need to be far more detailed. We're not talking about 10 classes anymore. We're talking about at least 100 probably. So here, the number of labels you're going to need, now we're talking about thousands. And if you go a step even further, that, for example, the same robot on the phone can actually help customers. They can actually solve their problems online right away. Then we're already talking about probably tens of thousands of labels. And why this is an especially complicated case is that when you talk to a chatbot, then when a chatbot gives you a small text box of about something that you weren't really asking about, then you can just tell it that no, I'm not interested. This is not it, and like you're confused because the bot didn't help you that much. But it's generally fine. But if you have to sit on the phone line, while the robot tells you like several lines in a really low speech, as they always do on the phone, then you can get really annoyed. So we have to be like far more certain when we're helping customers on the phone. Now, why all the effort? And what I mean by why all the effort is that why so much preparation or thinking about data specifically? And why is probably because it's one of those things that is under your control. You can do it, it's preparatory steps before actually launching the project. And it's probably one of the cheapest things you can do. Like thinking of the actual questions and thinking about the data you need to solve them is probably the cheapest way you can validate your idea or ensure that everything's going to go smoothly. Everything after that is gonna be far more complicated. And here, of course, like most people realize that developing models and engineering them is going to be expensive and a really resource-intensive process. But what people often don't think about is that validation, the model validation itself, is also going to be, can be quite complicated. Now, when we're talking about validation, validation is experimentation, and there are two kinds of validations or experimentations you can do. One of those is offline. Offline is what you can do on the data that you already have. So you can test on past data that if the model works or not. This works in some cases. For example, speech recognition. You can build a model and test it on the data you already have. But for example, with recommendation engines, it's simply not going to be feasible because the fact that a person didn't, for example, purchase something, doesn't mean that they wouldn't have purchased it. Like there are so many reasons why they didn't do it. Maybe they just didn't see that the object was present. Maybe they were unaware of this. Maybe it wasn't like in the forefront enough. So every kind of measurement that you do on a recommendation engine that's based on past data is inherently going to be at best indicative and indicative of the real-world results, but can also turn out to not be. So in these kind of cases, you have to do online validation, which is, again, this piloting, testing on actual people. And why I think that, why I'm saying that it can be very complicated is that if we're testing your recommendation engine and you have a really frequently visited page, you have, I don't know, hundreds of thousands of people visiting a day, then that's fine. But because like when we look at those, like, this is completely messed up, the slide. But for example, if we look at the sample sizes that you will need to check to see a certain amount of progress or difference between like the baseline and the probably improved model, we're talking about, like, let's say baseline is about 40% accuracy. Then if the model gets 50% better, then you need to test 400 people to be sure that you have actually, like, that the model is as much better as you're seeing. And the less the improvement, the larger the sample size will have to be for you to be able to detect that actually something went better. So if you have a baseline of 40%, but you are like hoping to increase it about 3 to 5%, you would need to test the model on at least 5,000 samples. And again, if it's a recommendation engine and you have a really frequently visited eShop, then that's fine. Like you can get those 5,000 in less than a day. But for example, like we're working also with the Estonian tax authority. And we're building classification models for them as well. So, and in their case, if you want to verify what the model is doing, you will have to actually go and look through through the data. Like a person has to check through every sample's data. And in that case, even 400 can take a long time and can be very expensive in both like money and people's time. So. Key points from all that I wanted to tell you. First, of course, is like ask the right question. Like this is where everything starts. If you have that right, then verify that your data has signal to like or is likely to have signal to answer the question that you found. Then confirm that the data is correct for the case that you're trying to solve. If you don't, then you need to get the right data. If the data is wrong, you're not going to get anything out of the project. Then also consider the labeling options, and not only if you already know that you're going to need more data, but like if you want to enhance the project at a later point, or maybe, or likely even, something is gonna come up during the project which shows you that if you had a bit different labeling, you could do a lot more with this project. So at least consider it, like where can you do this labeling? Do you have people for it? Are the people reliable? What the process is going to look like? So think about this. And assess complexity for data volume, meaning that assess the complexity of your problem, meaning that how many different classes you have, how easily separatable those classes are, how complex the problem is in general. Maybe find someone who can like consult you or help you with this question. But you should really understand how much data you actually need. So yeah, and with that I will conclude. Thank you for your time. I'm Markus. You can contact me on this email address.